Well, then if x were positive, e of x would be 0. If x were negative, it would be undefined, because you have 0 raised to a negative power. That would be reciprocal of 0, right? And the reciprocal of 0 is undefined. That would be bad. So we want b to be either between 0 and 1 or bigger than 1, right? And so we could have an example. Let's have an example. E of x is 2 to the x. That's a nice simple one, isn't it? So what does that do? Well, that doubles every time x increases by 1, right? Because you've got x factors of 2. So we could make a table of values and round up the usual small integers near 0. You're going to get 1/8, 1/4. So these are the reciprocals. Anything to the 0 power is 1. And you can see that, multiply by 2 at each step, right? Every time the input increases by 1, we get a number which is twice as large as what we had before. So it's repeated multiplication, right? And if we were to make a table, a graph from this table, here's the x-axis and the y-axis, here's 1, 2, that's not perfectly evenly spaced, I have to say. It's a little better. So, yeah. Okay. And so 1, 2, 3, 4, 5, 6, 7, 8. Perfectly evenly spaced. So 0, 1 is here. 1, 2 would be here then. 2, 4 would be there. 3, 8 would be up here. Going back to the left, we get half as much each time, right? So half of 1 is a half. That's going to be about there. Quarter, an eighth, and to connect the dots with a nice smooth curve, we get something like this, right? And that's a typical kind of exponential function shape. You notice that it's always positive, right? So the range is the interval from 0 to infinity. The domain, there's no restriction on the domain, is there? How about, what else can we say about this? It's strictly increasing. As you go to the left, you're going to go up. And you go up pretty steep, right? If you start going out here, things, you're doubling very large numbers. Pretty soon, you got very, very, very large numbers. So, if you put in 10, what's 2 to the 10th?
Or 096. So last one's 256, 512, 1024.
1024. Or 1024. That's obviously going to be over the roof somewhere. And that's only going out to about here, right? You're like in the stratosphere. Well, I don't know. But pretty far up. So how about there? Yeah, let's just leave it at that. Okay, so but this is kind of an interesting number here. 2 to the 10th is 1024. Which is approximately 1,000. It's 2.4% bigger than 1,000. And it's in computer science, that's a kilo. Kilobyte, for instance. Is it a kilobyte?
Mm-hmm.
Well, it could be. At least in the old days, when they said kilobyte, they meant 1,024 bytes. Kilo is a prefix in the metric system that means 1,000, right? Mm-hmm. So it's off a little bit, right? It wasn't quite a kilobyte, but that's what they called it. I use this sort of in the past tense because the problem is that if you've got, gigabyte, then you've got, 1,000 of these things, which is actually, so what, if you got 2 to the 20th, what's that? Well, that's going to be 2 to the 10th times 2 to the 10th, right? Property of exponents says when you have a common base, you add the exponents. And so if this is approximately 10 to the 3rd, then this is going to be approximately 10 to the 6th, right? Which is a million, so that'd be like a megabyte. But how big is a megabyte actually? Well, when you actually multiply 1,024 times 1,024, what are you going to get? Well, 16. Yeah. What was it here? Yeah, so 6, 17, 5, 9, 4, 0. And so you get, it's actually 4.9% bigger than a million. So almost 5% bigger. So a kilobyte is off by 2.4%, but a megabyte is off by almost 5%. And then when you go to gigabyte, you're off by even more, right? And it starts mattering, especially if you're producing these things and selling them, and you're selling them per kilobyte. Well, if we call the kilobyte actually 1,000 bytes, then we could sell the smaller thing for the same price. Anyway, right. So, and what you're seeing here is the effect of compounding, which is going to be a topic for today, right? Compound interest. So when something is growing at a certain rate, and the thing that's growing is growing naturally. So the larger it is, the faster it grows. Then the effective rate increases. Well, okay. So we'll see about that. All right. So anything else to say about this? Well, how about if the base were between, so this space here, B, is 2, right, which is bigger than 1. What if the base were between 0 and 1? What would an example of that be? Here's another example. Example 2, which is going to be E of x, let's say, is 1/2. So again, A is 1. Well, I would ask you to notice that this is 2 to the negative 1 to the x. And that, what's the rule when you have a power to the power? Well,
you multiply them, don't you?
Yeah, I mean, so I'm using the fact that 2 to the negative 1 is the reciprocal of 2, right? So I've already used that. So if I were to say, well, this is 1/2, that'd be back to here. But yeah, when you raise a power to the power, what do you do with the powers? Multiply them, right? I mean, it's a property of exponents, which we could review the properties of exponents, but that was for last term. Okay. Or the term before. Yeah. So this is the same as if I replace x by negative x here. And what does replacing x by negative x do? Well, you reflect across the y-axis, right? Y-axis there. So this point that was at 3/8 is then at negative 3/8, right? So I'm making a table of values here. There's a different function. It's got the same name as that function. Hope that's not confusing, but so now we're going to start at 8 and get half as much each time, right? Here the growth factor, if you like. So B is sometimes called the growth factor, because that's what you exponentiation is like repeated multiplication, right? So you keep multiplying by this factor B. How many times? Well, x times. What if x is not an integer? Well, yeah, we can extend that, right? So a half of 4 is 2, half of 2 is 1, half of 1 is a half, and you keep getting half as big. And notice that this is the same numbers in reverse order, right? So you get 1/8, and so this is decreasing exponentially. And approaching the x-axis asymptotically, right? So you notice that y equals 0 is a horizontal asymptote for this. So you never get to 0, right? It's like if you had a pile of sand and you kept chopping it, taking half of it, and half of what's left, and half of what's left. Eventually you're down to a single grain of sand, and then you chop that single grain in half, and you keep chopping the half in half. And eventually you get to an atom, one single atom of silicon, I guess is that what sand is made out of? Then you cut that atom, and the world explodes, because that's splitting the atom. Don't do that. Okay, so abstractly, though, there's no limit to how small a number we can make. We just keep cutting it in half and get smaller numbers. Don't worry about whether it's an atom or not. Just a number. Don't forget to label your answers. Okay? And so we see if the growth factor is bigger than 1, we have exponential growth. If the growth factor is smaller between 0 and 1, then we have what's called exponential decay, which is called decay partly because it's used to model radioactive decay. Radioactive decay works like this. Okay, so with that in mind, oh gosh. Well, yeah. So let's talk about other ways of writing this. So sometimes you see this. So what's different here? Well, instead of A, I've got this parameter E sub 0. And instead of B, I've got 1 plus R. So the reason we use E sub naught or E naught is because what's E of 0? Follow the order of operations. So do you multiply first or apply the exponent first?
I'll apply the exponent.
Yeah, so if you apply the exponent first, then 1 plus R, presumably we can raise that to the 0 power and get 1, and so it's E naught times 1, right? So that's E naught. That's why it's called E naught, because it's E of 0. Yeah?
Can you go a little bit more into detail about E naught? I mean, to me that looks like a logarithm, but you're saying that that's like...
Logarithm.
Well, yeah, because I'm trying to recall, like, or logarithms probably are written like exponents too then. Because I thought like when you were to write logarithm shorthand without putting log, I thought you just put the integer value down where you have the O right there in the E versus in the upper right, an exponent.
Yeah, so the base of a logarithm is often written as a subscript.
Right, yeah, that's what it was.
Yeah, but 0 can't be the base of a logarithm, right? Because the base of the exponent is also the base of a logarithm. Same thing. And so we won't be using 0 for that. Yeah, and so it's a common thing to use,
So to confirm, is that technically a logarithm, what you just put there? It's just
No.
a 0?
No, a logarithm is an exponent. So if you want a logarithm here, that's x. But we haven't talked about logarithms yet.
Yeah.
Oh,
If I were to solve for x, I would have to express it as a logarithm. So when you say E naught, that's this word, naught, which is kind of a Britishism. It comes from Cockney, which is no white. And what's a white? Well, a white is a farmer. So nobody, not even a farmer. I mean, you're talking about nobody, nothing, not.
So, sorry to jump in again. If you were
Yeah.
just take the not away in that top line, does that affect the outcome at all? I'm just wondering.
Oh, it's just notational, right?
Like, should I just assume E0 is the same thing as X or a
No,
different variable?
E naught is gonna be E of zero, right? And because when you plug in zero for X, that's what you're gonna get. That's why we call this E naught, because it's another name for E of zero. So it's a particular function value. It's the y-intercept, right? Yeah.
It's somewhat the same meaning as in physics where it means initially, like initial.
Yeah, sure, initial value, right, yeah. Okay, and so, R is called the growth rate. So we talked about the growth factor,